Okay, so next we have to discuss different methods of polarization of light, basically electromagnetic wave, and we have already discussed one method. So what is that method? So polarization by selective absorption. So this method we have already discussed. That is in case of a wire grid polarizer. The examples are wire grid polarizer or a Polaroid. So their light are polarized by using the concept of selective absorption or the phenomena called selective absorption, or is also called dichorism. That is selectively it absorbs some component of the electric field and transmit the other component of electric field. Okay, so that is the one way, and the second way is by reflection. So by reflecting a light, you can polarize it. And third one is, so if you can reflect, if you can produce a polarized light you through reflection, then obviously you can polarize light by refraction as well. Okay, so second is refraction, and the fourth one is a new thing to you, that is called double refraction. So it is an interesting phenomena. So certain crystals are showing this double refraction phenomena, basically quartz, tourmaline. So these kind of materials are showing double refraction quartz, and we have calcite. Okay, and the last one is the polarization by scattering. So here we will discuss the few of the methods. Okay, we already discussed one thing, that is selective absorption. We already discussed. Okay, now today we are going to discuss the other two, that is reflection and as well as refraction. Okay, so we are going to discuss this point and this point. Double refraction we will discuss later. Okay, so we can directly go to our topic, the polarization of light by reflection. So this can be easily explained by using one famous law. It is called Brewster's law. So what it says, suppose you have an interface, some air glass interface or air water interface, anything. You have air here, glass here. Okay, then we have some incident light. Okay, so if incident light, obviously there will be some portion will be transmitted and some portion would be refracted. Okay, so before that I have to just draw the normal to it. Okay, and this I can denote by some the angle of incidence. Usually we'll denote I, the angle of incidence. Okay, and the some portion of the light would be reflected, and the angle of incidence and the angle of reflection should be same according to the law of reflection. This must also be equal to I, and some portion of the light would be transmitted. So if it is moving from a rarer medium to denser medium, then the angle of refraction would be lesser than the angle of incidence. So that we already know. So that is why when I'm drawing the refracted ray, I've drawn the refracted ray close to normal, and the angle of refraction I drawn by symbol r. Okay, so these two are same, and I and R are connected using some formula. What is that formula? You might be remembering that formula. It's called Snell's law. What is Snell's law? N1 sine I equal to N2 sine R. And what is N1? N1 is the refractive index of the first medium, and N2 is the refractive index of the second medium. Okay, so N1 sine I equal to N2 sine R. So accordingly, so if N2 is greater than N1, so obviously R should be less than I. Okay, it's opposite. R should be less than I. Okay, now here till now I have not discussed any polarization here. Okay, we have just discussed the phenomena of reflection and refraction. Now, suppose you have incident an unpolarized light here. If you insert an unpolarized light, then your light will have both dot and arrow. Okay, so this dot is called the S polarization, and the double-sided arrow is a P polarization. Okay, then obviously in reflection, what would happen is usually it will contain dot. Our dot will dominate than arrow. What might be the reason? So you can give a simple explanation for it. So if you look at the oscillation of the P polarization here, the P polarization is oscillating like this. You can see the movement of the mouse point. Okay, the the P polarization are just oscillating like this. Now if it is coming forward, the P polarization will oscillate like this. And when during reflection, what would happen? The P polarization cannot go this way because the light is transverse wave. So there cannot be an oscillation of the electric field in the direction of propagation. Okay, so it is very difficult for P polarization to reflect. So usually what happens is in reflection, it will be dominated by S polarization, and P polarization would be very minimal. And at certain angle, what happens is at certain angle of incidence, the angle between the reflected ray and the refracted ray will become 90-degree at certain angle. At which angle that would be? That angle we'll call it as the Brewster's angle. So as at Brewster's angle, okay, let me denote by symbol IB. At Brewster's angle is become 90-degree. The angle between the reflected light and the transmitted light would become 90-degree, and you will get only dot. If I is not equal to IB, then what would happen? If I is not equal to IB, then obviously we'll have both polarization, the dot and arrow. Okay, if I is not equal to IB, if the angle of incidence is not equal to the Brewster's angle, then obviously there would be some portion of P polarization in the reflected light. Okay, and reflected light would be unpolarized. So here it is an unpolarized, is also become unpolarized. And obviously the transmitted light is always unpolarized. But the thing is, in case of transmitted light, the major portion of the dot would be reflected. So here, the intensity of dot would be slightly smaller. Okay, it may not have that much intensity, and the P have sufficient intensity. There will not be much problem for P polarization, but S polarization will have a lesser intensity. Okay. Now, if you change the angle of incidence, if you change the angle of incidence to the Brewster's angle IB, then this become 90 degree, and the reflected will contain only dot and no arrow. There will be only the S polarization and no P polarization. So that means your reflected light would become completely polarized. Reflected light become completely polarized, and this is called the Brewster's law. And so what we have done is we have just polarized light by reflection. So this is very easy to do. Suppose you have a glass slab and just incident light, and you have to incident light exactly at the Brewster's angle, then the reflected light would be completely polarized. So this is a very easy method and very cost effective method to polarize the light. Now the only issue is the amount of reflection is very minimum. So usually in the reflection through the glass, we'll get only 15 percentage, 15% of the light would be reflected, and around 85 percentage would be transmitted. Okay, so the intensity of the reflect light would be very small. Okay, so intensity would reduce drastically. So that is the one issue of this method. But anyhow, this is a very cost effective method. Okay, now we can find the expression for the Brewster's angle now. Okay, so when I equal to IB, this happens. When I equal to IB, we'll get the polarized light during the reflection. Okay, now how can you find the expression for IB, the Brewster's angle? So we can use the same Snell's law, the N1 sine IB equal to N2 sine R. Now, if you look at IB and R, the IB plus R must be equal to 90 degree, because this angle now become 90 degree. The angle between the angle between the refracted ray and the reflected ray is already 90. Then this IB plus R must be equal to 90. Okay, IB plus R must be equal to 90 degree, or R you can write 90 minus IB. So this become N2 sine 90 minus IB. Sin 90 minus IB is simply cos IB. We can write cos to the left side, so it becomes sin by cos, and sin by cos is tan of IB, and that would be equal to N2 by N1. So this is the mathematical expression for the Brewster's law, and IB is called the Brewster's angle. So we can calculate the Brewster's angle of any interface using this relation. So if you have an air glass interface, then IB is simply the N2. N2 is the refractive index of the glass divided by the refractive index of air. So usually the air, the refractive index will be taken as 1, and the different glass will have different refractive index. So around usual glass will have a refractive index around 1.5. Okay, so 1.5 by 1. So tan inverse of 1.5 would give the Brewster's angle for the glass air interface. Okay, and I think it will be around 57 degree. Okay, so for air glass interface, the IB is approximately 57 degree. Okay, and similarly, you can calculate for air, water, or any other interface. And glass also having different types of glasses, flint glass, crown glass, and obviously they will have the different refractive index. And you can calculate the Bruce's angle for the different material, or the different the interfaces. Okay, now this is one application. The application is by this Bruce's angle can be easily measured, and if you can measure the Bruce's angle, then you can use the information of the Bruce's angle to calculate the refractive index of a material. So that is interesting. So if you want to measure the refractive index of a material, you can find Bruce's angle. You can measure the Bruce's angle in the lab and calculate the refractive index. So what I have written here is, by knowing refractive index, we can how we can calculate IB, the Bruce's angle, and its reverse can also be done. If you know the Bruce's angle, you can calculate the refractive index. So that is one of the application of the Bruce's law. Okay, so that's all about the Bruce's law for the time being. Okay, so the Bruce's law can be used to produce a polarized light by reflection. So if you incident a light on in any interface at Brewster's angle, at its Brewster's angle, then the reflected light would be completely polarized. The reflected light will contain only S polarization. Okay, so here this dot is called S polarization. Now this has another interesting application. You can think about the cooling glasses. The cooling glasses usually we will wear, and we can have the cooling glasses with Polaroids. Okay, so usual cooling glasses is simply color films. Okay, it may not be Polaroid glasses, but if you use a Polaroid glasses, you can reduce the glare. How you can reduce the glare? Because the glare basically is a reflection from some surface. Okay, so suppose you are traveling in a sunny day, then it is possible that a large amount of light will come to your eye. Suppose you are driving on a sunny day. Okay, നല്ല നട്ടുച്ചയ്ക്ക് നിങ്ങൾ ട്രാവൽ ചെയ്യുകയാണെങ്കിലും സംഭവിക്കും ഒരുപാട് ലൈറ്റ് നമ്മുടെ കണ്ണിലേക്ക് വരും. അത് റെഡ്യൂസ് ചെയ്യാൻ ഏറ്റവും നല്ലത് സാധാ ഒരു ഗ്ലാസ് ധരിച്ചു കഴിഞ്ഞാൽ ഓക്കെ യു ക്യാൻ റെഡ്യൂസ് ഇറ്റ് ഫോർ സം amount. But if you use a Polaroid glass, you can reduce it to a large amount. How it can be done? Because നമ്മൾ യാത്ര ചെയ്യുമ്പോൾ അധികം നമ്മൾ കാണുന്നത് റിഫ്ലക്ട് ലൈറ്റുകളാണ്. ഓക്കെ, സോ ഇറ്റ് ഈസ് നോട്ട് ദ ലൈറ്റ് ഡയറക്ട്ലി കമ്മിങ് ഫ്രം സൺ. It is basically the light which is reflecting from the different surfaces. Okay, from uh, from some other car or some other vehicle, or from some other from a road, etc. Okay, so this reflected light usually contain S polarization. Now if you can block this S polarized light using a Polaroid, then what happens? The glare would be reduced much. We may not see much amount of glare. Okay, and that will protect your eye. So next time when you're going to purchase a cooling glass, better purchase a Polaroid glass, and it is slightly costlier. It will come around 3,000 to 5,000 rupees approximately. And uh, and there are ways to check whether the cooling glass is a Polaroid glass or not. Now that I already said to you how to check. How to check it? Just take a two Polaroid glasses and rotate one of it. If you rotate one of it, if it is a good Polaroid glass, then there will be complete extinction of light two times in a 360-degree rotation. Okay, അപ്പോൾ രണ്ട് ഗ്ലാസ് എടുക്കുക. ഓക്കെ, രണ്ട് കൂളിംഗ് ഗ്ലാസ് എടുക്കുക. You can take two cooling glasses and kept another cooling glass of same type and rotate one cooling glass and look some light source. Light source. then there will be the extinction of light two times. If you rotate it by 360-degree. Okay, so if that happens, then it is guaranteed that both glasses are Polaroid glasses. Otherwise, uh, either both would be non-Polaroid glass, or only one would be the Polaroid glass. Okay, so that happens. So you can check it if you purchase from a good shop and a good brand, you will not be cheated. Otherwise, there's a possibility that the people will cheat you. Okay, so the next time, I think when you're going to the shop, you will buy a good Polaroid glasses to protect your eyes. Okay, so those who are very interested in traveling, better purchase the Polaroid glass for your long-lasting eyes. The next is the topic is the polarization by refraction, and there is not much to say here. So the main portion we already discussed in the previous thing, the polarization by refraction. So this is basically the byproduct of the polarization by reflection. Okay, suppose you have a glass slab, a single glass slab, okay, and you incident a light, then if you incident the light in such a way that the angle of incidence is exactly equal to the Brewster's angle. Okay, so this would be the normal. So if this angle is the Brewster's angle, then obviously the reflected light would be completely polarized. Sunlight is unpolarized, and the reflected light would be completely polarized. But only thing is, the reflected light would have only 15 percentage of intensity compared to the incident light. 85 percentage would be transmitted. Okay, now what you can do is, if you look at this transmitted light, the transmitted light mainly contain arrow, and the dot would be very faint. Okay, the dot intensity would be very small. Now if you kept another glass slab parallel to the first glass slab, now again some 15 percentage of the dot will be transmitted. Okay, so for initially we have 85 percentage transmission. Now its 15 percentage is transmitted. Okay, so what is the 85 percentage of 85 percentage? Can take a calculator and calculate it. 72 percentage. So what would happen is the transmission would be 72 percentage. So 72 percentage would be transmitted, and again the transmission would dominated by arrow, and dot would be faint. And if you kept a glass slab again parallel to the first glass slab, reflected light would be completely polarized. And how much percentage would be transmitted? That would be 85 percentage of 72, and it would be around 60 percentage or 61 percentage. And if you have a very large number of such glass slab, if you have very large number of such glass slab, it is, I think one more may be enough. If you have a large number of such glass slabs, then finally the, the transmitted light will contain only double-sided arrow. The transmitted light will contain only the p polarization, and all s polarizations are completely reflected. Okay, so the 50 percentage of the incident light, okay, suppose the intensity is I, then the 50% of I, the intensity would be transmitted this side and 50% would be reflected this side. So this side will have S polarization dot, and here we have P polarization, which is a double-sided arrow. So this is the complete explanation of the polarization by refraction. Okay, so here the refracted light. So this is the refracted light, which is completely polarized. Okay, and this is basically just the application of the Brewster's law. There is a polarization by reflection. So therefore, there is no need of the much explanation required here. So if you kept the pile of glasses, okay, the pile of plates, okay, these are called pile of plates. If you take the larger number of such plates, then each time some portion of the light, some portion of the S polarization would be reflected, and after some point the refracted light will contain only the P polarization, and in that way we can polarize the refracted light. Okay, now there is one quantity you have to define here. The quantity is called the degree of polarization. Degree of polarization. Okay, so if IP and IS denotes the intensity of P polarized and S polarized component in the transmitted light. Okay, suppose so initially the total intensity is I, and the total intensity I will contain equal amount of P polarization and S polarization. So in here 15 percentage of the S polarized light is already um, reflected. Okay, so only 35 percentage of the S polarization would remain after that, and 50 percentage of P polarization would remain. Okay, so if IP and IS are intensities of transmitted P and S polarized light, then the degree of polarization denoted by symbol P is given by IP minus IS divided by IP plus IS. Okay, so this is for a single glass slab. So if you have many such glass slab, then what would happen is finally there is no IS at all. There is only IP. IS becomes zero. Okay, so this is what is called the degree of polarization. So when IS becomes zero, the P would become maxima. The P would become one. Okay, so when IS equal to zero, IP equal to 1. So that is the maximum value for the degree of polarization. Okay, when IP equal to IS, then there is no polarization at all because both are there, and the degree of polarization would be 0. Okay, so when IP equal to IS, the degree of polarization is 0. Okay, so that's it for today. Okay, so we have just discussed the two methods of polarization, the polarization by reflection and the polarization by refraction. The polarization by reflection is basically the application of Brewster's law. So this information can be used when you are going to purchase a new cooling glass. Okay, so that's it. And the second is refraction. So refraction is simply the byproduct of reflection. So if you kept a very large number of glass slabs, okay, the pile of plates, then all one type of polarization would be reflected, and only other type would be refracted, and the reflected light will become polarized. And only one thing is your incident light must incident at the Brewster's angle. So that is the important point. So refraction is also connected with Brewster's law. Okay, so that's it for today. So we can stop it here. And the next is we have to discuss the fourth type of polarization, which is through a double refraction. So we have to discuss, we have to introduce what is meant by double refraction, and its a small theory how the double refraction occurs, and how can we use this double refraction phenomena to polarize an electromagnetic wave. So those things we'll discuss in the next session. So thanks for watching. We'll see you in the next class.